welcome to this video. Today we're talking about investigating joint embedding predictive architectures for reinforcement learning. This paper was published by the University of Bielefeld 7 days ago, and the overall idea is to bring like a higher dimensional input and lower dimensional space with the JEPA architecture, which was first introduced by Jan LeCun from Meta. So let's just jump right into the abstract. Joint-Embedding Predictive Architectures, shortly JEPA, have recently become popular as promising architectures for self-supervised learning. Vision transformers have been trained using JEPA to produce embeddings from images and videos, which have been shown to be highly suitable for downstream tasks like classification and segmentation. In this paper, we show how to adapt the JEPA architecture to reinforcement learning from images. So we have like a reinforcement learning task as our downstream task, and the input in our reinforcement learning or from our reinforcement learning environment is like images and not just a low dimensional vector. We have images as our input, so high dimensional input. We discuss model collapse, show how to prevent it, and provide exemplary data on the classical cardboard task. So they show the cardboard test. If you're not familiar with the cardboard test, that's not a problem. I will just give you a small introduction to the cardboard task. So that's the task that our agent has to solve. The idea is that we have like a pole here in the middle, and we have a card, and the idea is that the pole is not allowed to fall down to the ground. If it falls down, the agent receives a reward of -1. As long as the pole is not falling down, the agent gets a reward of +1. And now the overall ideas, or the agent has the actions to go to the right or to the left. In this particular state, in this image, the agent has to choose right in order to drive the card to the right, that this one is not falling down here but going more to the left. So yeah, that's cardboard. It's a pretty basic reinforcement learning. It's environment. It's like the MNIST of reinforcement learning. And there are now many ways how you could embed this input, or this input from the simulation or output from the simulation into an embedding. For example, you could just choose to bring it into a 4-dimensional vector, and this would we would choose like the degree of the pole to the vertical line as one input for our vector. Then in the second dimension we would choose like the card position, and then for example the third dimension would be how fast our pole is falling down to the ground, and so on, so that we have at the end 4 dimensions. But the authors already mentioned that they want to use the whole image, and this brings us to a little more complex input data for our neural network. They're saying it also here directly in the introduction. In the classical cardboard test, the image state at a typical resolution has 400 times 600 times 3 dimensions. So 600 width, 400 height, and 3 for red, green, and blue. And this leads to over 700 to 2000 dimensions. So we have a very high dimensional input space. But the actual state given by the simulation only consists of card position, angular velocity, and angular velocity resulting in ds equal to 4. So we could actually just bring this very high dimensional input picture into a low dimensional space, into a 4-dimensional vector, and have the same information that is necessary for our reinforcement learning task. And now they say consequently it is desirable to learn a low dimensional representation from image on which reinforcement learning can take place. This representation has to capture all necessary information to master a given task. Toward this end, many techniques have been developed. One of the most famous is to use a variational autoencoder or just a normal autoencoder. So what's the idea of an autoencoder? So we want to bring this high dimensional space into a low dimensional space. This we could do it like very easily if we just flatten the whole image, and then we have, for example, here a very high dimensional space. So actually, yeah, this dimension, and we are now training a encoder. We could use CNNs, or we could then we have to take it as a image and not flattened, or we just use like MLP. And we bring it in a lower dimensional space. This space could be now like four dimensions. So here we have just 4 neurons at the end, and then we train to reconstruct the output. Okay, so we have a high dimensional input space, we bring it to the lower dimensional space, and then we want to reconstruct the high dimensional space. So the actually task is, if we have like here now a low dimensional input vector, we want to bring this vector back to the image itself. This brings a little problem with it, and for our downstream task, because now, as we can see on our image, we have like a lot of background information that's not important for our reinforcement learning task. But the reconstruction loss normally is like the L2 distance between this vector and this vector, and the reconstruction loss doesn't distinguish between the background or the important information, because we as humans know that this is the most important part of our image, so this here, and not the background information. But our L2 distance brings us the problem that each pixel has the same impact or the same importance for our reconstruction loss. And so we have like here not the most important information, but maybe just a lot of information in order to reconstruct the background, and then too less information for our actual task. So this is why architectures like autoencoders or variational autoencoders are bringing some problems with it. So just one sentence maybe to the difference between the autoencoder and the variational autoencoder. The variational autoencoder doesn't have like here absolute values. We sample from a distribution, and this should be a Gaussian distribution. Let's draw it again. Okay, we can clear this one. So we have like a Gaussian distribution, and with the mean and a variance. So mean and variance. So each vector consists of those two values, and then we sample from it, and also trying to reconstruct it. This brings a little bit more noise and has some other advantages, but also some disadvantages if you compare it to autoencoders. But yeah, the overall disadvantage of this architecture for reinforcement learning is again that each pixel has the same importance to our loss, and this is why we learn a lot of information for background for the background, but not a lot of information maybe for our real task that's important to solve for the reinforcement learning agent. Okay, so I think they are saying it also here. However, autoencoders have a key limitation, and that they assign equal value to every pixel. We spoke about it in the card pole example. That means that a white background pixel is equally important as a pixel of the pole. Also, the latter provides more relevant information. This can lead to results in which the relevant moving parts of the image are blurry and difficult to recognize, while the background is perfectly crisp. Okay, now to overcome this limitation, they regarding to Yann LeCun and the Joint-Embedding Predictive Architecture. We can see it in this figure, and maybe I will just explain a little bit how the JEPA architecture works. So we have two inputs here and a variable or like a latent input set. X and Y are both, for example, images, and one image is masked. This is our X image. Okay, so we have the X image, which is masked, and we have an X encoder, and the X encoder is like on the context encoder. And this one tries to bring our mask image into a into embedding space where we have a lot of information about or high dimensional information density about our image, in order that our predictor here can reconstruct the image without the mask. So the predictor should also reconstruct here the masking. And in order to achieve this, the X encoder has to take care that has to understand the picture in order to predict the mask right. Okay, but now there's one more trick, and the predictor is not trying to predict the pixel itself, but it also predicts a latent space, and this latent space comes from the Y encoder. So this is our target encoder, and the Y encoder takes as an input the wool image, so without masking. So without masking, you could also use different ideas or different tricks to corrupt those images, but basically on the right side, or the target encoder, which is this one, so target Y encoder, it always takes like the wool information, and the X encoder just takes less information than the Y encoder, and then tries to bring it in a embedding space and to predict the high information of the original input. And now the target encoder gives us also an embedding space. So we have like here a latent vector, and also here from our X encoder. And now we have a predictor, and this predictor is just an easy MLP, and this predictor now predicts to reconstruct the image, but not the pixel itself, but in the latent space. So we are not trying to predict every single pixel, we try to predict the embedding of our target encoder. And this brings the advantage with it. This brings us the advantage that maybe the target encoder not encode so much information about like the background pixel, but just about the information about the important pixel. And so we have like an encoder which tries to learn which information is really relevant about our input. And yeah, we are not trying to predict every single pixel independently. Okay, so that's the overall idea. But now, if you can see it, it can bring us some difficulties with it. And one, for example, is if the X encoder and Y encoder just learns to bring like for every batch, for every input image, we bring it to a like always to the same latent space. So we say always 1, 2, 3, 4, for example. So that's not how it works with certain numbers, but it's just an example. If we always bring it to 1, 2, 3, 4 in our embedding space, and here also the predictor can do a very easily task to predict it. It just predict the same, and then our loss is very low. So maybe to make it clear, we have here the loss calculated, and the loss is backpropagated here and also here. But if we do it simultaneously, the encoder and Y encoder can learn to just bring it to like, for example, this latent space, and then our model actually collapses. So we have a very low loss, but everything is embedded into the same vector region. Okay, so this is why normally you just backpropagate the loss from here to the predictor in X encoder, and the Y encoder is not updated every step, but you're doing a exponential moving average of those rates. Okay, so maybe after 1000 steps, that's not exponential, so there are several ways you could do it. You can say after 1000 steps, or you do it every step, but you do an exponential average. For example, with 1000 steps, we train our encoder 1000 for 1000 steps, and then we update our Y encoder weights with this. Okay, with the weights of our X encoders, and not with this not with those gradients. And this is how you could prevent model collapse. Okay. I think they are also saying it here. The downside is that it's much more prone to collapse, yeah, since a constant output of the context and target encoders along with a predictor that performs an identity operation will result in a minimal loss. Okay, so if we bring it here to the same very basic embedding, we can just do a identity mapping as a predictor, and we have a very low loss, but actually the model didn't learn anything. So, in this paper we show how to adapt JEPA to reinforcement learning problems that can be described as a low-dimensional state. By this refer to problems like Atari games. Yeah, okay, we explain in detail how to use a vision transformer in tandem with JEPA to learn embeddings which can be used for successful reinforcement learning. We discuss model collapse and scenarios and how to avoid it. Okay, we already talked about model collapse, and they also show another way how to avoid the model collapse. We will look at it later, and we show exemplary data using the classical cardboard task. Okay, so I think we can jump to the methods. So let's have a look at figure number 2. It's actually the same as this figure, but now it's tailored for the downstream task. And we see again here our X input or our X encoder, which is our context encoder. On the right side we have our target encoder. And now we also have two different inputs in our encoders. And the left input, our context encoder, gets a current image, the image from the state t-1 and the state t-2. So the last three states, or the last state, the state before, and the current state I'm in. And the Y target, the target encoder, gets the current state of the image, the state I was before, and the state I will go to, so t+1. And now the idea is that the task, so this encoder has to learn to guess or make a prediction. So the predictor is here. The predictor has to predict, given a very good embedding from the context encoder, to predict also the t+1 image. Okay, and this makes it even harder to learn and has more information. And the author shows to do a very basic MLP task. So this very basic MLP neural network here, in order to have the most part about the prediction already in the in this encoder. Okay, so that this encoder has not so much strength, or this predictor has not so much strength, and just gets like the embedding, and in the embedding from the context encoder there should be the most information already within, and then it just makes a pretty basic prediction with an MLP. Okay, and then we see on the left side our actor and our critic, and this is our reinforcement learning agent, and they chose to train this with PPO. So we have an actor, and the actor has learns a policy given a state S, how likely is an action A, and then we have a critic which learns an advantage. The overall idea is, okay, given a state S, how much reward can I get, I'm currently in state S, how much reward do I expect from this reward going on, okay, from this state going on. Yeah, and then you do like your reinforcement learning PPO update. I will not go into it deeper in this video. But now you can see we can train our encoder here. So this encoder, we could also train it with this and this gradient and also this gradient, okay? So we have a lot of inputs or a lot of gradients in order to update our encoder. And here they're just explaining a little bit why they also chose to give, for example, the Y encoder here, so our target encoder, not just T+1, because this would be enough. They also give the input T and T-1. This is they chose this because they didn't want to change the architecture of the vision transformer, but normally you don't have to change too much, so I guess it would be possible. But yeah, they did it for simplicity, I guess, to just have the same model here and the same model here, so they both get the same input. Okay, and yeah, they try to they use the vision transformer. I think yeah, they are saying here that they did like the Euclidean distance. We already talked about this, so here the Euclidean distance. One more maybe important input about the vision transformer, so the VIT. You put your image into, you bring your image into patches. For example, each image can be broken up into 16 times 16 patches, and we have it like 3 times. And then we have like several encoder, vision transformer encoder blocks where we put all the tokens through. And at the end, the question is, are we using the classification token? So for example, we could just add one more token, and this token should have all the informations that are important from all the other tokens. Or the other way we could do it, we put all tokens into our predictor model, and the author chose to just doing the classification token, which most of which is like the standard way to do it, I would say. So you just have one token, and therefore the token, if you would put all your tokens into the predictor model, we have like a huge space, and if you just put in the class token, we have not so big space. Actually, our input then is just the input of our just one vector, so how long our classification vector is, and our classification vector has the same length as our classification token has the same length as our embedding dimension of our model. Okay, so yeah, so that's how they did this. And I think we can just jump to one more learning objective in order to prevent the collapse we talked about. So the JEPA architecture brings the risk with it that it can collapse, and they added one more loss. And the idea of this loss is that our embeddings that are learned from our context encoder, so this is our X encoder. We do it like for, I don't know, if we have 64 samples and we do it as like in a batch, then we have 64 tokens here, or 64 vectors here. Okay, so 64 classification tokens, and now we are calculating the variance for each dimension, and if the variance is too low, then we could argue that the model collapsed, and we don't want to we want to prevent it from collapsing, and this is why we add the variance to the loss, so the encoder also learns to not bring all all the classifications tokens just into the same region, and so our model would collapse, because now it's not possible, or we make it harder, because in the loss is now a term which regards to the variance of our classification tokens, and we want to have the variance high but also not too high. This is why we clamp it here with 1, so 1 is our maximum. Okay, now for the vision transformer we have like not just one loss, we add all the losses together. So we have the loss of our actor, we have the loss of our critic, we have the loss of our regularization, so this loss, and also the JEPA loss. Okay, so this one is L2 distance, this one comes from the PPO, and L reg comes from the regularization. So I guess we could just jump into the results. It's not visible so clearly, but most important, so this orange line here, I will do it now in this orange line here is the one which is trained both with JEPA and the gradients from the actor and critic. So they use in the orange part the gradients, so let's just clear it a little. They use the gradients from the actor and critic and the gradients from this loss in order to update the encoder, and this results in the best average episodic return. So it goes like this, and if we compare to the other, they are all much worse. So if you want to read the results, or want to read the conclusion of something, I will not reading it now. I will put the link into the paper into the description. I think it was a pretty cool paper, just to have a quick remind how JEPA works, and they show it for the cardball task. I hope you enjoyed this video, and hope we see us in the next paper review.